So the second case for consistent systems is the case where the system has infinitely many solutions. So in this case, we say that the coefficient matrix can be row reduced or is row equivalent to a row reduced echelon form. But this row reduced echelon form is not the identity matrix. So similar to that first illustration that we looked at with row reduced echelon form, right, it is still reduced all the way down, meeting all 5 conditions, but it doesn't have a 1 along the main diagonal in each one of those pivot positions. So your coefficient matrix is row equivalent to a non-identity row reduced echelon form. And in addition to this, the entries of your solution vector x can be one of 2 things. So we say that the entries of the solution vector x may be either a basic variable, like we just saw with case 1. So remember, the basic variables are associated with the pivot positions. So an entry in the solution vector may be a basic variable, i.e. a pivot position, or the entry may be a free variable. So the free variable is what produces the infinitely many solutions. So in other words, a free variable is associated with a non-pivot position. So let's think of an illustration here to help us better understand how we're producing infinitely many solutions. So for example, let's think about a augmented matrix here in row reduced echelon form, but not the identity. So let's say we have 1, 0, 2, 3, 0, 1, minus 4, 5, 0, 0, 0, 0. Alrighty, so here we go. So looking at your coefficient matrix here, we can see that x sub 1 is associated with a basic variable. It has a pivot. X sub 2 also has a pivot, but notice that there's no pivot position in x sub 3. So we'll make a love note here to ourselves that x sub 1 and x sub 2 are pivots, or basic variables, because they are pivot positions. But x sub 3 is not a basic variable. Now you have to be careful here when checking. This might not always hold true. Notice here how x sub 3 does not have a pivot, but if you look above it, there are still x sub 3 entries. This is what implies or lets us know that x sub 3 is a free variable. The solution depends on the value of x sub 3. So we can even add here that x sub 3 is some real number, some scalar value. This is what's going to produce those infinitely many solutions. So to help us see those infinitely many solutions, we need to think about the general solution to the system. So what is this matrix in row reduced echelon form telling us? Well, let's just simply rewrite each row as it is. So row number 1 says that x sub 1 plus 0 of x sub 2 plus 2 of x sub 3 is equal to 3. The second row is telling us that 0 of x sub 1 plus 1 of x sub 2 minus 4 of x sub 3 is equal to 5. And row 3 here is all zeros, so we don't even consider it. So notice here, I've included zeros in my system, but we don't even really need those. Those we can kind of get rid of. So let's rewrite this below, giving ourselves a little bit more room. So we can say that this solution here, this augmented matrix, is saying that x sub 1 plus 2x sub 3 is equal to 3, and that x sub 2 minus 4x sub 3 is equal to 5. And we want to solve this for those basic variables. So this is equivalent to x sub 1 is equal to 3 minus 2 times x sub 3. X sub 2 is equal to 5 plus 4x sub 3. And now we can add that x sub 3 is free. It's a real number or scalar value. So this is what the augmented matrix is telling us in our linear equation form. But now we want to find our parametric description of this. We want to think about the general solution vector. So the parametric description of the general solution is as follows. So we know here that the system, again, is depending on each entry. So your solution vector, vector x, is in R3. Got x sub 1, x sub 2, x sub 3. And now we want to use the solution defined in its linear equation form to define this solution vector. So we know that x sub 1 is equal to 3 minus 2x sub 3. So we have 3 minus 2x sub 3. We know that x sub 2 is equal to 5 plus 4 times x sub 3. So plugging that in, that's 5 plus 4 times x sub 3. And x sub 3 is free. So we're going to line up an arbitrary x sub 3 under that column. And if it helps you, incorporate a 0 here. So we can't leave our general solution like this. We need to break it up into pieces. So we want to break it up into this column vector of constants. And then you want a column vector for the free variable. So this breaks down, this breaks down to, again, that constant vector, 3, 5, 0. Plus the column vector for x sub 3, or free variable. So that's minus 2x sub 3, 4x sub 3, x sub 3. But again, we wouldn't leave it like this. We wouldn't want to leave our final answer like this on a test. Wink, wink. You have to pull the basic variable out, or excuse me, the free variable out. So your beautiful final answer, the parametric description, vector x sub 1, 2, and 3, is defined by the constant column 3, 5, 0, plus you have a scalar multiple in the x sub 3 column. X sub 3 is your scalar multiple because it is free. It's a constant. Pull it out. So this is x sub 3 multiplied by the column vector negative 2, 4, 1. And don't forget, this is, of course, such that x sub 3 is a scalar. So this is the final answer, the parametric description of your general solution. And you can see here, because x sub 3 is real, it's a scalar value, you can choose a numerical value for x sub 3 to produce a particular solution. So this emphasizes all possible solutions. But if I was to ask you, use this now to find a particular solution, you simply need to choose a value for x sub 3. So to find a particular solution, you need to choose a specific numerical value for x sub 3. So choose a numerical value for x sub 3. And let's be lazy mathematicians for a moment, trying to do this in the most efficient and effective way as possible. Let's let x sub 3 be 0. Okay, so then one possible solution would be 3, 5, 0 plus 0 times -2, 4, 1. Now be careful here because we're working with vectors. So this 0 times a vector reduces to the 0 vector. So technically we could think about this as the column vector, and we'll write this out just this first time through. So this reduces to 3, 5, 0 plus the 0 vector. So that's just the vector with 0 entries. So to get that beautiful final answer, we add the like entries. So we have 3 plus 0 equals 3. 5 plus 0 equals 5, and 0 plus 0 is 0. So this is one particular solution to the system. So this is that particular solution. It's not the only one, because as we saw above, there are infinitely many solutions. So when we keep this solution vector in its parametric form, as we have done in this case, we can see all possible solutions. Versus with a particular solution, you choose one numerical value for that free variable to find one specific solution to that given system.